Welcome back, teachers. Section 12.2 or 12-2 and Miss Wilson here to help you out. All right, so we're going to jump right in with an example. If you haven't watched 12-2 part 1, go back and watch it. Okay, now what we're doing here is we're going to prove that a quadrilateral in which the diagonals are congruent and bisect each other is really a rectangle. Okay, now let's think about what that means and what we would really have to prove to have a rectangle. It says if ABCD is a quadrilateral whose I can't say it, whose diagonals bisect each other, it is a parallelogram. Now if you go back and look at your properties, and let's see what they're asking us to do. So we're going to prove that a quadrilateral in which the diagonals are congruent. Okay, so this is something we know, and bisect each other is a rectangle. So we know that the diagonals are congruent and they bisect each other. So it says if ABC CD is a quadrilateral whose diagonals bisect each other, if you look at your properties of parallelograms, you will see right off the bat it's a parallelogram. So we've proven that we have a parallelogram. Okay, so we started with a quadrilateral with some conditions. Right off the bat, one of those conditions told us we have a parallelogram. And that means a lot. You remember what a parallelogram means? A whole lot of things. First of all, that these lines are parallel. Okay, so BC is parallel to AD and BA is parallel to CD. Now, before I get deep into that, we're supposed to show that one of the angles in ABCD is a right angle. If we can show that one of them is a right angle, will that work for all of them? We'll talk about that too. Now, like a previous problem we did, we're going to go through the proof and break it down to make sure it makes sense. You've got to really buy into this. So it's saying that angle BAD, okay, so let's find it. Angle BAD, trying to highlight it, BAD, down here, okay. Angle BAD and CDA, going to highlight that one as well. So CDA are supplements because ABCD is a parallelogram. Remember we talked about that even true for a trapezoid, that the corresponding angles are supplementary. They add to 180 degrees. Okay? All right, so that's true for a parallelogram as well. Now, triangle ABD and triangle DCA. So once again, I'm going to erase what we have here and then highlight. So triangle ABD, so ABD, so there's the triangle in purple, and triangle DCA. And I'm highlighting that one in green, so DCA. There we go. So they cross over each other by side, since AB is congruent to DC. So first of all, let's look at that. Why do we know that AB is congruent to DC? Because it's a parallelogram, remember? And we proved it was a parallelogram earlier because the diagonals bisected each other. Right. Okay, so we know this is a parallelogram. So BA and CD are congruent. Opposite sides of a parallelogram are congruent. Hey, they said it there. Good. And AD is congruent to DA. So here's AD. And that's congruent to DA. Okay, remember that's the same part of the triangle. So, of course, they're congruent to each other. And BD is congruent to CA. So BD over here, okay, that's the diagonal, is congruent to CA. Now, how do we know those are congruent? And then to answer that question, you said, because they told us that, Miss Wilson. They told us that in the setup of the problem. So we know that BD is congruent to CA, okay, and because it said the diagonals are congruent. Okay, therefore, here we go, triangle BAD, B-A-D. Okay, so B-A-D is congruent to C-D-A. Again, why is this? What are you supposed to answer there? Right? Are you completely lost? That's okay. So this is saying angle BAD. Let's take a look at it. Angle BAD is congruent to angle CDA. We know that this angle and this angle are congruent. Why do we know that? Well, we just proved, because we had side, 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 that those triangles are congruent. That means every single part of those triangles are congruent. That corresponding parts of congruent triangles are congruent. There you go. So that's why angle BAD is congruent to CDA. Now, it says since these angles are supplementary, what does that mean? Remember, they said it way earlier that angle A over here, okay, which is really BAD, angle bad, and CDA are supplementary because you're dealing with, that's one of the properties of a trapezoid, that complementary angles add to 180 degrees. So they add, so if you added them up, the measures would equal 180 degrees. But now, y'all, if they're the same, and they add to 180 degrees, does that mean we could just divide that by 2 to find out what they're equal to? Oh, that means they're each equal to 90 degrees, and that's what we were trying to prove. So that one's 90, and that one's 90, okay? And we also know that that one's 90 and that one's 90. How could we argue that all of them are 90? Well, how about because it's a parallelogram, right? Remember, the opposite angles are congruent. So if that's 90, then that guy over there's got to be 90 also. And if this one's 90, then this guy over here has to be 90 also. So there we go. We proved that it was a rectangle. At least we followed every step to prove it was a rectangle. So we have another proof, example 8. Again, we're just going to try to break this down, make sure this argument makes sense to us. So it says in the figure of triangle ABC, so that's the big triangle. It says it's a right triangle, and CD is a median. So this line, I'm going to highlight it for you right here, that's what we call a median, and it defines it here for us. It's a segment joining a vertex to the midpoint of the opposite side. Now, what we know right off the bat then, if that's the midpoint of the opposite side, that means AD and DB are congruent, right? Now, it says to the hypotenuse AB. Now, that's the hypotenuse over there, which means my right angle is right there at angle C. Now, here's what they want us to do. They want us to prove that the median to the hypotenuse in a right triangle is half as long as the hypotenuse. So they're saying my green highlighted line is half as long as this line over here, AB. Okay? So, let's see if we can follow along with their proof. Now, I know you've noticed this, but whenever you're trying to conduct a proof on your own, or even follow a proof, you need to know what you're trying to do. So, they set it up for us. We are given that angle C is a right angle. I really like to draw my right angle in there. That's a right angle. And D is the midpoint of AB. So D is in the middle. We need to show that, we need to prove that 2CD is equal to AB. Again, that twice CD is equal to AB. And that's what they said, that 2 of these is equal to the hypotenuse AB. So that's our ultimate goal. That's all we have to do. Okay? Now, check out this picture. That might not be intuitively something that you thought to do that'll get the job done, but it does. So here we go. We're going to extend CD to obtain CE. Okay, so CE is 2 CDs. So basically we just extended it, and we're saying that this length is the same as this length. Moreover, remember, this length is the same as this length, because that's what a median does, is it divides that hypotenuse in this case in half. Alright, let's keep going. Now let's follow this argument. It says because D is the midpoint of AB. Okay, so D, remember, is the midpoint of AB. That's the definition of a median. Okay, then I've got the 2 marks there to show that it's the midpoint. The diagonals, okay, I left out a line. D is the midpoint of AB. I've got that marked. And also the midpoint of CE. And it says by construction. Remember, they did that on purpose. They drew DE to be as long as CD. Okay, so that's what it says by construction. The diagonals of ACBE, so the entire quadrilateral, okay, bisect each other. Why do we know that? Because it's already constructed that way. This was the median, so that cut that one in half, and then we drew this one that way. So these diagonals bisect each other, and ACBE is a parallelogram. Remember, if diagonals bisect each other, that's a given for a parallelogram, as long as you have a quadrilateral, okay? So we know that. That's a parallelogram. Now it says since angle C is a right angle, remember we knew it was a right angle, that was given, okay? Then ACBE is a rectangle. This whole thing is a rectangle. So remember, if you have a parallelogram that has a right angle, we just proved that they're all going to be right angles, okay? So it's going to give you a rectangle. Now, if you go back and look at the properties of a rectangle, the diagonals of a rectangle are congruent. So what does that mean? That means CE is the same length as AB. Okay, we know that. Therefore, check this out, 2 CDs, okay, so 2 CDs, which is the same as CE. So that's the same as saying CE. 2 CDs is CE. By construction, so 2 CD is equal to AB, and that's another way of saying that CD is half of AB, and that's what we were trying to prove, right? And so that's my little sign for end of this proof. Again, are you thinking, how in the world would I come up with that on my own? Not necessarily, but follow the proof. Make sure you understand every line. If you didn't, mute me and go back and just look at this and make sure it makes sense to you, okay? All right, because I'm just explaining how it makes sense to me, and hopefully that'll help you out. Now here's an interesting topic. It refers to the idea of a construction backing up our properties. Remember, we did a construction for side, side, side. We did a construction for side, angle, side. And we did construction for angle, side, angle, and angle, angle, side. Well, they discuss a construction in terms of a quadrilateral. It says one way to determine a quadrilateral is to give directions for drawing it. It says start with a side and tell by what angle to turn at the end of each side to draw the next side. So I'm going to try to do a rough one here, again with a squiggly looking squiggly screen. It's kind of hard. But we draw a line. Ooh! Let's get my pen working. Let's try it again. So I'm going to draw a line. Okay? Now it says start with a side and tell by what angle to turn at the end of each side to draw the next side. Okay, so in your mind, what they're trying to say is an exterior angle. So keep this line going in your mind, okay, and then we're going to turn. So if I said turn 30 degrees, then we would turn 30 degrees, okay? So that would be the 30 degrees that we're talking about, okay? And say we're supposed to turn again. Now, you'd have to keep going with this line, okay, and we have an exterior angle. Let me try to say it that way. External angle, exterior angle. You know, what the hey, it works. All right, so let's turn some odd degrees. I don't want to pick degrees to turn because I could tell you wrong that many degrees and it won't add up right, and we don't want to do that. Okay, so let's say we turned, or maybe I do. Let's say we turn, what do you think that is? About 90 degrees? Let's say we turn 90 degrees, the exterior angle. Okay, now this is a quadrilateral, so we have to turn again at some point. Now I'm supposed to keep going with that line to figure out what angle it's going to be. And let's turn again. It can only have 4 sides, so I have to come back here. We could figure out that angle, couldn't we? I turned 30. I turned 90. Okay, what did I turn here? Well, don't get caught up in it because I would need to know this angle as well. So I would need that other angle over here. So let's just say we turned, I don't know, that looks like over 90 degrees, say 110 degrees. Okay, and then got us back here, and then we could calculate what that degree is, because remember all the exterior angles add to be 360. I wasn't trying to go that deep with it. I was just trying to explain what they meant about the exterior angle. But the point we're trying to make here is that a side, angle, side, angle, side. That's what you're doing. You drew a side, then you drew an angle. Then you drew a side, and then an angle, and then a side, and then an angle. Okay, and then a side. Seems to be a valid congruence condition for quadrilaterals. This condition can be proved by dividing a quadrilateral into triangles using what we know about congruence of triangles. So this could turn into a proof as well. I'm not going to do it. I'm going to spare you that. You've looked at a lot of proof in this section, but it's an interesting topic to show that side, angle, side, angle, side would prove congruence of a quadrilateral. We've done all of our congruence with triangles, right? Okay, so let's wrap up this topic and let's move on to some homework. And I've picked these homework just to kind of help you focus your mind on what we just learned. So homework example 1, which is very similar to some of the assigned homework problems. For each of the following additions, is it possible to construct two non-congruent triangles? Explain why or why not. Okay, so think about in terms of construction. Now remember, in construction, what have we done so far? We constructed a side, side, side situation, and then we used that to show that two triangles were congruent. We did a side, angle, side situation. Again, we did some construction, and we showed that two triangles were congruent. We also have what? We have angle, angle, side, and we have angle, side, angle. And these are in no particular order, but that's what we have. Okay? Now, we have a triangle A, a triangle with angles measuring 55 degrees and 65 degrees, and a non-included angle side of 6 centimeters on a side of the 55-degree angle. Okay? So when I look at that, we've got a 55 and a 65. So that's an angle-angle situation. So it's not one of the first two for sure. It's an angle-angle situation. But it's not the side in between. So I would argue that that is, we've got a side, 6 centimeters, on the same side as the 55 degrees, and then you have a 65 degrees. These are the three things we know. To me, that is a side, angle, angle. Okay, now you might be looking at that and going, we don't have a side, angle, angle. But y'all, angle, angle, side really is a side, angle, angle. Okay, because that would just connect up on the other side. So can we draw two non-congruent triangles? No. There's only going to be one triangle that fits this bill. Just one. So there's no way we could draw two non-congruent triangles. Let's try this again. Okay, so I have a triangle with angles measuring 55 degrees, 65 degrees, and an included side of 6 centimeters. So that means I have 55, and then a 6 centimeter side, and then a 65-degree angle. Now you can attempt to draw these on your own. I'm just kind of listing it because it's enough for me to see what's going on. But if you want to try to draw something close to this, that may help you out. Now, what do I got going on? Well, I got two angles again. But this is clearly an angle, the side in between, an angle. And it even says the included side. So can we do this? Yes, there is a triangle that exists. Is there more than one triangle that exists? No. There's just one. You could do a construction with that. So we're not going to find two non-congruent triangles. If we do true triangles, they're going to be congruent. That's the only way I can draw it. Okay? Well, what about the third one? What if I had a triangle with angles 55 degrees, 65 degrees, and 60 degrees? Well, that's an angle, angle, angle situation. What do you think about that? Well, the first thing you should think is that it's not on our list, right? How about I could draw 55 degrees, 65 degrees, say up there, and then 60 degrees over there, or I could draw one like that. That's the thing. When you have three angles, you can scale it up or down. They are what we call similar triangles, and we plan to go into that into more detail. But you don't get the exact construction. You don't know how long any of the sides are, so how do you scale it whatsoever? So the answer is yes, this is possible because there's more than one triangle. There's an infinite number of triangles that have 55 degrees, 65 degrees, and 60 degrees. The teeny ones and huge ones. Okay? So again, how do you know, or how do I know, what I can use to show triangle congruence? Again, just let me remind you, you can use side, side, side. If you know the lengths of three sides of a triangle, and you know it is a triangle that really exists, then you can show congruence to another triangle, or you can use construction to draw it. What else? If you had side, angle, side, same story. If you had angle, angle, side, and you had angle, side, angle. In other words, the side in between two angles, or back up here, the angle between two sides. What you could not do is a side, side, angle. Okay, that's out. You can't show congruence with side, side angles. There are some particular situations, like hypotenuse leg fits in that category, but this is a special case that works, whereas side, side angle just in general doesn't work. Okay, another one is angle, angle, angle. There's an infinite amount of those cases. You cannot use that to either construct or to show congruence. Okay, now a little bit extra to talk about those two guys you can't do. It says, why does side, side angle and angle, angle, angle do not work as congruence shortcuts? And this is based on construction. Look at what's going on here. So we have a side, side angle. I think you see that in this situation. Now, if I were to try to construct it, look, I have my 11, okay, and then I have my 30 degrees over here, but this 6 here can go in two different places. You can build two different triangles with the situation going on. So it could be at this particular angle or at this particular angle and still meet up with that 30-degree angle. That's why you would have two different options for your answer. Therefore, you could not construct using this, and you can't show congruence. And what about the angle, angle, angle situation? We talked about it, but you see right here, okay, then you have angle Z, angle Y, and angle X. They're all the same angles, but this triangle is bigger than this one. Now, later we'll talk about those being similar triangles, but not congruent. You can't say that they're the same exact size. Now, this is straight out of the homework. It says the diagonals of one kite are congruent to the diagonals of another kite. Okay, so what they're saying here is this line on another kite is the same length, and then this diagonal on another kite is the same length. From that information, can you conclude that the kites are congruent? Why or why not? Okay, now I'm not going to give you all the details here, but it's something I want you to think about. I kind of sat and thought about it for a little while, and I thought enough about it that I thought maybe we should talk about it together. Okay, so I mean, at first thought, if you thought, okay, I've got this diagonal and this diagonal, that you can't make a different kite with that. That's pretty fixed, right? But wrong. Let me show you what you could do. So, and it took a kite in front of me to realize what's going on here. I really had to look at one hard. The problem that showed up in the homework did not have a kite in front of me. And so I had to look at one and go, oh, wait. You know what you could do? You could just slide that diagonal that way. It would stay the same length. This diagonal would stay the same length, but the shape of the kite wouldn't be the same, right? Just picture sliding it that way, okay? Keep it perpendicular. Keep that 90-degree angle, because remember, one of the diagonals bisects the other one and meets at a 90-degree angle, okay? So what I did is I went ahead and played with this particular kite, and I slid it up for you. So I took this diagonal and I slid it the way that I showed you, north, up, and there we go. Okay, and so how I really did that, I'm working in PowerPoint, and I just copied these lines. So I copied that line and moved it over here, and I copied the diagonal and moved it over there. I slid it up like that, reconnected, and that's a completely different kite. So even though you have congruent diagonals, that is certainly not enough to show congruence between two kites. I thought you might find that interesting. I really had to look at it hard to make sure I was comfortable with that answer. If you have any other questions, please let me know. I hope you have a great day, and this concludes section 12-2.